Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on Theory of Numbers, lecture number 43, in which I will solve some problems on Euler's theorem. Now, we solve a problem. Problem is find inverse of 2 modulo 9. Let n equal to 9 and phi be the Euler's phi function. Therefore, phi 9 equal to phi 3 square equal to 3 square multiply 1 minus 1 by 3 equal to 3 square multiply 2 by 3 equal to 3 cancel, 3 2s are 6. This is number 1. Let A equal to 2. Therefore, GCD of A n equal to GCD of 2 and 9. This is equal to 1. This is number 2. Therefore, by Euler's theorem, 2 to the power phi 9 is congruent to 1 modulo 9, implies that 2 to the power 6 is congruent to 1 modulo 9, implies that 2 multiplied by 2 to the power 5 is congruent to 1 modulo 9. Therefore, 2 to the power 5 is the inverse of 2 modulo 9. Since 2 to the power 5 equal to 32, when 32 is divided by 9, we get remainder 5. That is, 32 is congruent to 5 modulo 9. Therefore, 5 is inverse of 2 modulo 9. We may check this, since 2 multiply 5 equal to 10, which is divided by 9, we get remainder 1 modulo 9. Therefore, inverse of 2 modulo 9 is 5. This is answer. Now we solve the next problem. Problem is, with the help of Euler's theorem, solve Ax is congruent to B modulo M with GCD of A and M equal to 1. Given that GCD of A and M equal to 1. This is number 1. And AX is congruent to B modulo M. This is number 2. Since GCD of A and M equal to 1, therefore by Euler's theorem, A to the power phi m is congruent to 1 modulo m. This is number 3. Multiplying both sides by x, we get A to the power phi m multiply x congruent to x modulo m. This is number 4. Multiplying by A to the power phi m minus 1 in 2. We get A to the power phi m minus 1 multiply A x is congruent to A to the power phi m minus 1 multiply B modulo m. Implies that A to the power phi m multiply x congruent to A to the power phi m minus 1 multiply B modulo m. Let this is number 5. From 4 and 5, we get, here we see that in left side A to the power phi m multiply x congruent x modulo m. Here also same left side, and right side is another thing, A to the power phi m minus 1 multiply B modulo m. Therefore, x is congruent to A to the power phi m minus 1 multiply B modulo m. This is the required solution. Now we solve the next problem. Problem is solve the linear congruence using Euler's theorem. 5x is congruent to 3 modulo 14. Since given that 5x is congruent to 3 modulo 14, since GCD of 5 and 14 equal to 1. This is number 1, this is number 2. Since by Euler's theorem, the solution is x is congruent to A means 5 to the power phi m is 14 minus 1 multiply B B is 3 modulo 14. This is number 3. Since phi 14 equal to phi 2 multiply 7 equal to 2 multiply 7 multiply 1 minus half multiply 1 minus 1 by 7. This equal to 2 multiply 7 multiply 1 by 2 multiply 6 by 7 equal to 6. This is number 4. Using 4 in theory, we get x is congruent to 5 to the power 6 minus 1 multiply 3 modulo 14 implies that x is congruent to 5 to the power 5 multiply 3 modulo 14 implies that x is congruent to 5 to the power 5 multiply 3 equal to 9375 modulo 14. If we divide 9375 by 14, we get remainder 9. So we may write x is congruent to, this is 9 modulo 14. Therefore, this is the required solution. Now we solve the next problem. Problem is find reduced residue system modulo 2 to the power m where m is a positive integer. Now we solve this. Since 2 is an even integer and m is a positive integer, implies that 2 to the power m is an even integer. Therefore, positive integers not exceeding 2 to the power m and they are relatively prime to 2 to the power m be odd integers 1, 3, 5 dot 2 to the power m minus 1. Therefore, reduced residue system modulo 2 to the power m be 1, 3, 5 dot 2 to the power m minus 1. Now we solve the next problem. Problem is find unit digit of 3 to the power 1000 by means of Euler's theorem. We know that when any integer is divided by 10, the remainder is the unit digit of that integer. For example, let we have 324. If we divide this integer by 10, here we get 30 to 4, here 2, 20 and remains 4. So 4 is the unit digit. Hence we may conclude that the unit digit of any integer is residue modulo 10. Since GCD of 3 and 10 equal to 1, therefore by Euler's theorem, 3 to the power Euler's phi function of 10 is congruent to 1 modulo 10. This is number 1. Since Euler's phi function of 10 equal to phi 2 multiply 5 equal to 2 multiply 5 multiply 1 minus half multiply 1 minus 1 by 5. This is 2 multiply 5 multiply half multiply 4 by 5 equal to 4. This is number 2. Using 2 in 1, we get 3 to the power 4 is congruent to 1 modulo 10, implies that 3 to the power 4 to the power 125 is congruent to 1 to the power 125 modulo 10, implies that 300,000 is congruent to 1 modulo 10. This means when 3 to the power 1000 is divided by 10, we get remainder 1. Therefore, when 3 to the power 1000 is divided by 10, we get remainder 1. Therefore, unit digit of 3 to the power 1000 is 1. Now we solve the next problem. Next problem is find a reduced residue system modulo A number 9, B number 16, C number 18. Firstly we solve A number. Positive integers not exceeding 9 are 1, 2, 3, 4, 5, 6, 7, 8, 9. Positive integers not exceeding 9 and they are relatively prime to 9 are 1, 2, 4, 5, 8. Therefore, reduced residue system modulo 9b 1, 2, 4, 5, 8. Now we solve B number. B. Positive integers not exceeding 16 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Positive integers not exceeding 16 and they are prime to 16 are 1, 3, 5, 7, 9, 11, 13, 15. Therefore, reduced residue system modulo 16 B 1, 3, 5, 7, 9, 11, 13, 15. Now we solve for number C. Positive integers not exceeding 18 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Positive integers not exceeding 18 and they are relatively prime to 18 are 1, 5, 7, 11, 13, 17. Therefore, reduced residue system modulo 18 B 1, 5, 7, 11, 13, 17. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.